Hi. Today we're going to continue our several lectures on optimal taxation, and we're going to do a variation of the important model of Lucas and Stokoe that we talked about earlier in a couple lectures. And what we're going to do is we're going to take exactly the same economic setting in terms of the physical economy that Lucas and Stokoe described and analyzed, but we're going to make one change, and it's going to be an important change. The change is going to be, instead of having state contingent debt, either in the form of Arrow de Bruce securities, if we do it time zero style, Arrow de Bruce style, or Arrow security style, if we do it sequentially, we're going to have only one, we're going to have incomplete markets. In particular, we're going to have the government and the private agents only being able to trade a risk-free one-period bond. Our purpose in doing this is to follow the paper by Iagari and others in an effort to explore how the Lucas and Stokoe model could be altered to bring it closer to Barrow's famous 1979 paper, in which he got a characterization of optimal taxation that was very different than Lucas and Stokoe's. And one way to read the Lucas and Stokoe paper is an attempt to recover in a more explicit framework some of the outcomes that Barrow had asserted in his 1979 JPE paper. The striking outcome, one of Barrow's striking outcome, was that regardless of the stochastic process for government expenditures, tax collections should be a random walk. Lucas and Stokoe did not find that. They found that tax collection and tax rates should have, in their Markov setting, stochastic properties very similar to those of government expenditures. So they failed to recover Barrow's striking results about taxes being a random walk regardless of the stochastic process for government expenditures. And there's after Lucas and Stokoe's paper came out for almost 20 years, there was a conjecture that Barrow must have had in mind incomplete markets. And maybe if you radically close down enough markets, you could get closer to Barrow. But that was a conjecture, and it was difficult to analyze. And this was pointed out in an important paper by Chari and Keogh, that studying optimal taxation problems, Ramsey problems, using the approach of Lucas and Stokoe would be very difficult in incomplete markets models, because of the additional restrictions that incomplete markets models impose on the Ramsey allocation. And so today we're going to confront that difficulty and see what we can do with it. So here's where we're going to go. So, as we say, many of the features of this economy are going to be exactly like those of Lucas and Stokoe. And by the way, material that I'm using can be found in two places. One is in the revised version of chapter 16, and the other is in the, again, revised version of the lecture on the AMSS model that's in the Quanticon website. And today I'm just going to lecture from the Quanticon website. Okay, so some boilerplate stuff. We're going to have a history, and for most of this talk, we'll think of this history of a state ST as being driven by a Markov process. That's not exactly necessary, but it'll be convenient at certain places, especially computationally. Because it's going to turn out that this model, as Chari and Keogh warned us, is going to be a difficult one to tackle computationally, unless we use a tool which Chari and Keogh didn't pursue, namely dynamic programming squared. So we're going to come back to that. So we're going to have government expenditures be just like we did part of the Lucas-Stokey lecture. They're going to be an exact function of S. And then now here we're going to have to make this. We're going to let consumption, leisure, and the labor supply all be time-dependent functions of the history of the state. And history dependence is going to play a role here that's not going to go away, even if the state is Markov. And the history dependence is going to be inherited from the incompleteness of markets. So there's going to be a representative agent, just like Lucas and Stokey. This is all a reminder. It's going to be able to divide one unit of time each period between labor and leisure. There's going to be output is going to be equal to the amount of labor that the representative household supplies, and it can be divided between consumption and government expenditures. And again, I'm making that's a subscript T and that's a superscript T. We're gonna make to stress some features of the model. We're gonna make, just like Lucas and Stokey did, we're gonna make government expenditures a function of the Markov state. Actually, we're even gonna make this a time invariant function of the Markov state in the work that we do. And then we have the representative agent. Pi t is the joint distribution over sequence ST. That's going to be the setup. And now that's going to all be common. But now what we're going to have is we're going to have risk-free one-period debt only. So the way we're going to characterize this risk-free debt is we're going to write it in a way that we're going to exploit the notation extensively. So in particular, look at this notation. Bt plus 1 S as a function of the history up to ST is the amount of time T plus 1 consumption good that at time T the government has promised to pay. And this can depends on ST, but not ST plus 1. And this means it's risk-free. It's a risk-free promise from the point of view of time T. We're going to let RT of ST be the gross interest rate on risk-free one-period debt between those two periods. And we're going to allow transfers. They're going to play a subtle role only in the very long run in this model. Okay, so again, the risk-free character of this is characterized by the dependence that we built into this function, or this sequence of functions. So the market value of the government debt is, at time t, is equal to the promised value divided by the gross one-period interest rate. So now the government's going to have a sequence at every history. It's going to have at every date and every history, it's going to have a budget constraint that looks like this. So this is the amount it owes when it comes into the period. That was decided last period. It's going to levy flat rate distorting tax on labor, and it's going to collect this amount. So those are its revenues. And then deducted from its revenues are government expenditures. Those are exogenous, just like Lucas and Stokke. We're going to allow transfers. These are only going to occur near plus infinity, if at all. If at all. Stay tuned for that. We might see that later. Okay. So that, and then an additional source of revenue is going to be the amount of risk-free government debt that the government sells that's due tomorrow. It's one period, and that's the gross interest rate. So what we're gonna do is we're gonna write it this way, and ZT, that history-dependent thing, is going to be the net of interest government surplus, net of these interest payments. That's the government budget constraint. And we're going to assume that the government is subject to a natural debt limit. This is going to be the weakest possible debt limit that's consistent with the environment. Okay, so there's going to be the first order condition for a household who trades only risk-free debt is going to be this consumption Euler equation. That's going to look like this. This is an example of the asset pricing equation where E of M times the rate of return is equal to 1. It's just one instance of that. Okay, so the stochastic discount factor in this model is beta times the ratios of marginal utilities. So that's the first order condition for the household. So we're going to substitute the first order condition. We're going to substitute, now we're going to do the following, the standard steps for a Ramsey problem. We're going to use a first order approach. We're going to use the household's first order conditions to eliminate prices and taxes from the government's budget constraints and the household's budget constraint. So we're going to entirely apply the first order approach, just like Lucas and Stokke, to the Ramsey problem. Okay, so if we do that substitution, we get this difference equation expressing government debt due today in terms of risk-free government debts that's going to be due tomorrow. This is a difference equation. It's tempting to solve it forward, which we will. So we'll just go through some mechanics. It's described a little bit here, but you've all solved difference equations forward. If you have not, tell me and I'll give you some notes on it. But just by repeated substitution, here's the first step. If we repeatedly substitute and we invoke the natural debt limit to rule out a Ponzi scheme, we're going to get the following expression, which is a classic one. The value of government debt is going to be, this is an interesting expression. It's going to be equal to the present discounted value of the, on the right-hand side, this is the present discounted value of the government surplus, evaluated at what prices? Well, those would be Arrow-Debreu prices in this economy, starting the economy at time t. If you go back and, so see chapter 8, those are pulled right out of those. That formula agrees exactly with what was in chapter 8 for the Arrow-Debreu prices. But here, notice the following. Here, we don't have complete markets. We have incomplete markets. So we're going to have to think hard about this. So there's a lot embedded in this equation. Now, the first thing to notice in this equation is there's something peculiar. Now, we got this using entirely legitimate operations. Again, we just took we took this budget constraint, we took this formula for the interest rate, and then we repeatedly solved for the same equation. So there's no sleight of hand here. But suddenly, what should be Arrow-Debreu prices have appeared here. And just a note, when I say Arrow-Debreu prices versus Arrow security prices, I'm relying on you being familiar with the material that's in chapter 8 of RMT. If you want me to put a version of that chapter on, I will. Okay. So there's a mystery. We're working with complete markets, but suddenly this we're working with incomplete markets, but suddenly this complete markets object has manifested itself. But now let's stare at this. Let's read carefully. Okay, so the first thing is, this object is a present value using Arrow-Debreu prices, what would be Arrow-Debreu prices, conditioning on time t information that would be the history of the state up to t. But notice this that's the right-hand side. The left-hand side, this is something that depends only on st-1 information. So this looks like something that might in principle be difficult to guarantee, because the object on the right is permitted to be a function of the history up to time t. The object on the left can only be a function of the history up to time t-1. So what this is telling us is that with incomplete markets, we have to it has to be true that this entire object must be measurable with respect to st-1. And that's the force of the incomplete markets. So what's going to turn out to be true is that what incomplete markets is going to do in this setting, it's going to restrict allocations or functions of allocations, Ramsey allocations. It's going to restrict those functions that in the Lucas-Stokes economy could be measurable with respect to st. That would be permitted in the Lucas-Stokes economy. It's going to require that they be measurable with respect to st-1. And that's all going to be part and parcel of only being able to trade in risk-free securities. And the incomplete markets literature of the 1990s talked about things like this in terms of having to project allocations onto the marketable subspace. And the marketable subspace in the Lucas-Stokes model was S superscript t, whereas in our model, it's going to be S superscript T minus 1. Okay. Anyway, this is kind of a little bit, might seem to be a digression, but it's pointing out that the essence of this model is all in this equation. Okay, so now we're gonna just follow some steps that we pursue, some additional steps that we always do with a Ramsey problem. In particular, we're going to substitute the resource constraint into the net of interest government budget surplus. And we're going to use the household's first order condition to eliminate the labor tax rate. And we're going to just re-express the government net of interest surplus entirely in terms of the allocation and stuff that's exogenous, except for this possible lump sum tax sequence. So if we substitute this expression, and for most of the analysis, we're going to actually set this equal to 0. Much of it could be set to 0. We'll come back to that. So our earlier equation becomes essentially a version of what we've done. It's the we're going to get a collection of implementability constraints that are inherited from the sequence of government budget constraints. They're going to look like this for time t equals 0, and they're going to look like this for time t greater than or equal to 1. So again, this budget constraint, this first one, this implementability constraint, this was the single one that was in the Lucas-Stokey model. This is the unique implementability constraint that was in the Lucas and Stokey model. But now we have an uncountable number, well, yeah, a huge number, because we have one for every history, of additional implementability constraints, which I've written kind of in a lazy way. I've replaced summations over conditional probabilities with this notation that's hazardous. You have to be very careful with it. E condition on 0 and E condition on t. And the key thing is that means ET means conditional on S superscript t. That's what we mean. So again, this object, which is a function, it's permitted to be a function of things dated t and greater, has to be an exact, that linear combination has to be, or that nonlinear combination of all that stuff in Z has to be measurable with respect to st minus 1. So this has to hold for every history and for every t. So incomplete markets, what it does is it adds to the original Lucas and Stokey implementability constraint this additional restriction on allocations. And Chari and Kehoe, in their 1990s paper, must have recognized this and said, this is a huge number of additional implementability constraints, and it really complicates seems to complicate the problem relative to the nice Lucas and Stokey characterization. So, okay. So what we're going to do now is we're going to write down, we're going to pose the Ramsey problem without state contingent debt. And what are we going to do? Well, we've basically set up what we have to do. We've eliminated taxes and prices in favor of the allocation. We have the implementability constraints now, not one constraint. on the allocation. And so what we're going to do now is we're going to choose an allocation. But now, and we're going to use feasibility to eliminate NT. So the allocation is going to be entirely expressed in terms of CT. So we're going to choose an allocation. But now we're also going to have to choose something else. We're going to have to choose a sequence of borrowings, one-period borrowings. And this second object, if you go back and review what we did when we did solve the Lucas-Stochastic problem, that was not there. But this is going to be here, and this is going to essentially have to track the measurability constraints. This is a bookkeeping trick to make sure that the measurability constraints are respected. So the maximization is going to be subject to this restriction. This is the Lucas and Stokey. And these additional implementability constraints, which look like this, that this object dated t has to be it actually has to turn out to be a function only of st minus 1. Okay. So this is going to take a little digesting if you're like me when I was studying this. And you might think, how on earth are you going to go about solving a problem like this? Maybe it gives you headaches thinking about it. Okay, so what we're going to do, and it actually gave me headaches, but then I went to a talk in the early 90s by Albert Marcet, where he was describing an approach that looked like it would handle this like a charm. So that's what we're going to see now. We're going to formulate a Lagrangian. So what are we going to do? We're going to kind of do it undergraduate style, if you will. We're going to first let gamma 0 be a non-negative Lagrange multiplier on the Lucas and Stokey constraint. This one up here. Well, we already had that Lagrange multiplier in an earlier lecture. But now, and we had this, that was our phi. That was our phi earlier. In earlier lectures. Or in this dynamic programming squared lecture, it was phi 0 and phi 1, but they turned out to be equal. So, but now, what we're going to have to do is we're going to actually have a whole stochastic process of Lagrange multipliers, and we're going to attach those to these. So we're going to put gamma t of st on there. And there's some technicalities which you can read about on whether or not those bind. And for most of the time, most of the things we're going to say, they are going to bind. They're going to be non-negative. Okay. So there's some discussion of this in the chapter and here. But for now, you could just think of them being binding. Okay. So now what we're going to do is we're going to form a Lagrangian. And then we're gonna transform it. So here's the Lagrangian. There's our objective function. We're gonna put this sum's gonna go from t equals 0. We're gonna put, so there's a conditional expectation at time 0. These are expectations at time t, just like they should be. So now we have a much larger number of implementability constraints. And here's our gamma. Okay, so what we're going to use is we're going to use we use something called Abel's summation formulation, and I think about this as this is discrete time integration by parts. And this, by the way, is a key step in Albert Marcet's paper with Ramon Miramon that I saw in the early 90s. So what we're going to do is we're going to transform this. You can verify this, that this is equal to this if we define this variable psi, which is going to look like this. It's going to be equal to its value last time plus the multiplier, and we're going to start out this psi minus 1 equal to 0. So if you just write this sum out, you'll see these two things are equal. And here's what you do. You just, if you literally write this out right here and use the law of iterated expectations, you'll find that this second term can be written like this. So the magic thing is ET has disappeared, and E0 of ET is E0. We're using that. Okay. So now, so that's our Lagrangian. So we're using these two things. And we have this interesting thing. This is gonna play a role, because remember how we started this. We said Lucas and Stokke wrote their paper because they couldn't understand Barrow, because Barrow was claiming a bunch of things were random walks, and they did their analysis, and there was a random walk nowhere in sight in Lucas and Stokke. Well, this thing isn't quite a random walk, but kind of has the form of it, depending on what gamma t looks like. And remember, psi t is a stochastic process, gamma t is a stochastic process. We're going to have to know what gamma t is going to look like. Okay, so that's just loose talk, but we'll come back to it. So now what we're going to do is, what do? We're going to take first order conditions with respect to CT. There's zillions of them. And we're going to take first order conditions with respect to this thing. Now, see, now I have this gamma t. This is an increment. Gamma t is the increment. Actually, good class to take is stochastic calculus. Comes in really handy. That's an increment in this psi. And what this tells us is, if you look at this, this tells you that gamma t plus 1 is an increment to a risk adjusted martingale, where that's a risk adjustment. Just file that. These days I have martingales on my head, but that's my problem. Okay, we'll come back to that. This is a conditional expectation of something is 0, and this is some kind of an adjustment. Okay. Okay, so now we see, so here's what's going to happen. So here's some preaching about the differences between this and the Lucas and Stokke economy. You'll see, well, this looks a lot, this equation looks a lot like the so compare this with the conditions that we got in the Lucas and Stokke economy. Remember, in the Lucas and Stokke economy, there was something that looked like, well, psi, if psi was phi, then this looks a lot like Lucas and Stokey. But phi was a constant in the Lucas and Stokey. And here, psi moves around. Well, we know how it moves around. Well, it moves around if gamma is ever binding. But if gamma is ever non-negative. But gamma will be non-negative whenever the measurability constraint is binding. Remember, gamma is the restriction on the measurability constraint, on this constraint. And whenever the restriction that we can only issue risk-free debt binds, gamma's going to be non-negative. So again, staring this. So if this were constant, this would look just like the Lucas and Stokey model, but it's not constant. And furthermore, if gamma were always zero, so phi will only be zero. Phi will only be constant if psi is zero. If gamma is zero, sorry. Psi will only be constant, phi, if gamma is zero. And if gamma is zero, then this term is out of there. And then this looks just like Lucas and Stokey. But in general, it's not. And furthermore, in general, it's not. And now allocations are actually going to be a function of b st minus 1 anytime gamma is not zero. Okay, so that's what this preaching is about. And then the second thing is the Lagrange multiplier in general can change over time in response to realizations of the state. Okay, so now we're at a situation where let's think of ourselves as a computational economist or pencil and paper economists, and we want to extract the implications of this model. Remember, we got a long way in the Markov case in solving the Lucas and Stokey model almost by hand. So what would we have to solve here? Well, we have these equations that are like Lucas and Stokey. But now we have this equation and this equation as well. And of course, we also have to solve the constraints. So we'll have to guarantee that that's true and that that's true for every t. So these equations I put star on, those are the equations we're going to have to solve if we take the first order approach to this model. And you can actually get somewhere doing that. And the AMSS paper actually took a direct attack on that. And it essentially worked. It tried to solve this in the space of sequences. And there's some discussion of this in chapter 16 now. I'm not going to pursue it here because I think there's a superior approach using dynamic programming squared. And that's what I'm going to talk about next time when I move on to the second part of this lecture. We're going to Bellmanize this problem. And we'll start there next time.